module makers. We have Christian Combs from Huasun. Christian is a director of business development Europe, and he is going to talk about designing heterojunction modules for various applications. Of course, reliability being the subtopic of his presentation. So, Christian, the floor is yours.
Hello, and thank you, Shravan. I hope you can hear me well and you can see me well. I'm going to share my screen now. So, can you see my screen well?
Yes.
Perfect. So thank you, everyone. Maybe some of you know me. I've been in the industry for a while, and I always have a keen eye for reliability. This is something that has been in the industry a topic that has become more and more important because we have become one of the main sources of energy in the world. And this means that everything has to work perfectly. I'm not going to bore you with some company presentation that is just standard. So let's go at the topic. First, I want to explain for those who are maybe not familiar with it, what is a heterojunction cell and a heterojunction module. The difference is basically at cell level that we use two materials. The first one, the main one, is the heterojunction. In the heterojunction is a crystalline wafer. So that is of type N. And on top of that wafer, we put successive layers of amorphous or microcrystalline silicon, and at the top and at the bottom, we put a TCO, which means transparent conductive oxide. This is a conductive layer that takes the electricity out of the cell. This has many characteristics, and some of them you can read them on the slide. I'm not going to just read them out, but some of them will come into play later when we talk about reliability. This cell structure is not new. It has been invented in 1997 and has been on the market ever since with very, very good results, especially about reliability. If you compare the structure of heterojunction to PERC, which is, let's say, on the way out, and TOPCon, which is the mainstream these days for utility scale at least, you see that the characteristics are uniformly better for heterojunction. And this is why Huasun has focused on this technology, and our company is only producing heterojunction modules and cells. So you see that efficiency is higher in real life. You may have seen some presentations based on the science of it that give a higher efficiency to TOPCon, but the reality of the production is that heterojunction modules show higher efficiency in production in the modules that you can buy for the same sizes. Something that is better is the bifaciality. Right now, we are at average 88% for production compared to average 79 or 80% for TOPCon. And the temperature coefficient is better. As you can see with these numbers, we consider heterojunction, generally speaking, to be a technology that is a little bit better than TOPCon. So we expect this to be the main technology in photovoltaics in the next years. So we can start a small bet now. There was a graph at the beginning that showed heterojunction at something like 10 or 15% of the global market by 2028, I think. I don't remember exactly who showed that. Probably it was Lars at the beginning. I'm going to put now my bet on the table and say that it's going to be more than 50% at that time. If we look at the modules, then there is no actual news. This is now more of a corporate thing. As Huasun, we think that different sizes of modules are good for different applications. So we offer from the small module less than 2 square meters to the biggest modules for utility scale over 3 square meters. In that sense, we offer as well the two different cell shapes, both the full square cut in two. This is the largest module with over 700 watt of output power already today, and the one that has rectangular cell, which in our case, we call it G10, but in reality, it has 210 millimeter of height. So it is comparable in the format to what, for instance, Trina earlier has shown, and they called it G12, because we have, for this utility scale module, 132 half-cut cells to improve the performance against hotspots. So there's basically every format. So it's going to be quite handy when we compare LCOE, because we can always compare one-to-one with the same configuration of TOPCon, with the same size of cells and the same size of modules. I want to go slightly over the different applications, because that was the title of the presentation. So I don't want to disappoint everyone who expected that. Sorry, there's somebody in the background. Thank you. So the key point of residential is that every customer has a different point of view and a different thing that is important to them. Some customers will look at the appearance. In heterojunction, we offer all black modules. Some customers want very high efficiency. Some others want the best performance. And this really good news about heterojunction is that we can be at the top of each one of these fields. So we think that this is the module of choice for such an application. I will not just read the slides. You can see that basically it really tops every single part of the palette of options that the customer have. This is how the all black looks. And let me just go on to the commercial roofs. In commercial roofs, we are a little bit in between. Some of the customers have some specific need. For instance, they want a module that is mounted on the short sides, then they choose a smaller module. Or some customer want to have just the best LCOE, and then they go to a larger module. So we offer different sizes and different module characteristics for this market. And now we start to say things about LCOE. And when we change to utility scale, that is obviously the main point. If you go to utility scale applications, LCOE is the first, the second, and the third characteristic that you want to improve and have the best. So I'm going to spend some time now talking about LCOE. But before that, I want to bring again the topic of the module sizes. As you see, we have two module sizes and two cell sizes, both the rectangular and the complete square cell, or cell cut in two, that originally square. And the point here is that in the market, many manufacturers entered in the last 2 years kind of a war or a fight about what is the best size of a module. And many manufacturers that started with 182 millimeter wafers have told time and again that that is the best. And some manufacturers who have produced 210 millimeter modules say the same, but from the other size. We do both, so we don't have the big stakes on this. So the customer that is convinced about one side is fine for us. We see this very clearly, that if you have a flat side with very large utility scale project, maybe 50 or 100 megawatt, probably the 210 millimeter wafers are the best for you. If you have a site where maybe the ground is not so stable, maybe there is some inclination, or maybe the ground is very soft, in that case, it is possible that you don't want to handle vertical pallets. In that case, probably the rectangular cell size is better for you, because the pallet will be more horizontal, more stable, and you can handle that in a better way in that case. Regardless of that, we offer both, so it is for you to choose. Now for LCOE, we are just going to get all three sizes and just compare them the same way. We have the classic 182, the rectangular, and the 210 millimeter. And for all of them, if you go back to this slide, you can see that our output power for each one of the sizes, there is a small overlap with TOPCon. This means that our lowest efficiency modules are equal to the highest efficiency modules of TOPCon. This is kind of the advantage of heterojunction in terms of efficiency and output power. When you put that into LCOE calculation, you can save some money in the installation. We have done this for an example project in Spain, so typical weather in Europe. And we have seen that the reduction of cost applies obviously just to a few points, not to the inverters. And this is a very conservative approach. And we see that we save around about ½ cent. Or we don't save it, you save it, or the EPC is going to save it. This is the advantage in CapEx. If we look into the yield advantage, this is a more complicated, more nuanced, but also larger difference. So here we have the advantage of the higher yield due to lower temperature coefficient, and the one that is related to the to the higher bifaciality. So as I said, currently we have 88% bifaciality in our production line. However, for this comparison, we have taken only 86%, just to be very conservative. In this plant that is based on utility scale, on trackers, we have reached an advantage that is equivalent to having about 1 cent, a little bit more than 1 cent lower capex. This equivalency, if you want, I can explain more, is based on having the yield of one system compared to the yield of a different system. So if our system performs, I'm going to say, 1% better than the comparative system, that this means that you would need the other system to be 1% larger in terms of nominal nameplate performance to reach the same as yield as our system. And that is how 1% higher total system means 1% higher expenses. In this way, we calculate the equivalent savings due to better performance. We have also included the better warranty that we have in heteroreaction compared to the standard TOPCon. And this has been weighted because on the first year is 1% for both, but in the successive years, there is a small advantage. And this has to be calculated, weighted year on year. So it's not just a total amount of better energy, but the energy that is in the future. Everybody who is doing LCOE will know that energy in the future becomes less important in the LCOE calculation. So we take this into account. We didn't want to make a calculation here that shows everything in the best light. I would have taken a system maybe in Dubai instead of a system in Spain. And this is, I think, quite realistic. So if you put these both things together, you get a natural advantage of heteroreaction over TOPCon. And keep in mind, I'm not comparing to monoperc. I think we don't need to kick that dead horse anymore. But compared to TOPCon, you see a natural advantage of more than 1 cent, 1.5 cents. And now the key point why we are talking here is because the cost difference from TOPCon to heteroreaction is today already lower than this 1.5 cents. And this is when heteroreaction becomes interesting for utility scale. I remember a webinar just a couple of weeks ago where the person was asking, kind of surprised, to my colleague Tracy, who was doing the presentation, oh, you want to go to utility scale, but what is your cost difference? And we were stating that we will match within some months, not years, the cost of TOPCon. So our expectation is that by the second half of next year, our cost of manufacturing will be comparable to TOPCon. So this is the place where I think it's quite important to everyone attending today or everybody in the industry to get acquainted with heteroreaction, because we believe that having an LCOE advantage that is really quite large and having a cost position that is going to be quite similar compared to TOPCon will mean that the share of heteroreaction on the real market will grow exponentially within next year. Many market analysts always are very cautious about the substitution of one technology with the other because they put, I don't know, 5 or 6 or 7 years scenarios. But we think that the brutal and extremely quick adoption of TOPCon on the market within this year shows that the market is advancing very fast. The technology changes are coming very quickly, and this will apply to heteroreaction. That is our opinion within next year. And now we go to talk about reliability. This has been the topic of the presentations here, and we want to do that too. So the way we go at it is in a very general approach that we look at every degradation mechanism, and we try to see what it causes and how to minimize it. Fortunately, we don't come from zero. You don't see it right now. Maybe let me try to I hope I don't destroy the presentation. Let me try to see. No, I cannot do that. Behind me, you don't see it. If I do this, maybe now you can see it. No. There is a heterojunction module that was manufactured in 2003 by the company Sanyo at the time. Heterojunction is not new, and the modules from Sanyo and then Panasonic that have been installed on the market are performing very well even today, 20 years later. So we don't come from nothing. We come from a technology that has been proven, and we have been improving on top of it. If you talk about the different ways that a module and a cell can get some degradation, we start with mechanical reliability. The key point that we have, if you remember, maybe it's not so easy, the first slide I was showing with heterojunction, we have a very flexible cell because our wafer is A, very thin, and B, it is not scribed with laser. The third point is that we do everything on the cell at maximum 200 degrees Celsius, so we don't damage the cell in manufacturing, and it is a really, really sturdy cell. The second point is what has been, I think, 80% of the discussion of today about the humidity ingress in the cell. For this, we have the glass backsheet. It's not a backsheet, the glass background. Anyway, you know what I mean. And in order to even more increase this, we use a sealant on the edges of the cell and in the holes of the glass where the junction boxes come. We think that it is very, very important to protect against humidity. It's not the same degradation method as TOPCon. This has been clearly explained by the people from GS Solar, by Ignacio, and by the first one, by Lars. But it is as well a concern because the TCO is a transparent conductive oxide at the edge of the cell, and we want to avoid corrosion on that area. I want to say that, again, we are not starting from zero. And if you look at modules 20 years, even with backsheet made by Sanyo at the time, and even with just EVA encapsulant, they are working perfectly today in so many places. So it is not like you should be scared. It is just a place where we want to be very, very good with you. About LID, LTID, maybe this is a dead horse. I don't want to kick any more N-type. So this is extremely well controlled degradation. PID is something specific to heterojunction. PID is related to the polarization of the surface of the cells. So many carriers are going to be maybe accumulating at the edge of the cell because they interact with the glass surface and the polarization may happen in that way. For heterojunction, it doesn't happen. That doesn't happen because we have a transparent conductive oxide at the edge of the cell. This means when the carriers would accumulate in the surface, they are already in a conductive layer. So this means they're subject to the electrical field that will take them away from the cell. So this is something that we don't see as a degradation source. Finally, about UV, this is a concern by everybody. This was maybe the other 10% of the discussion today. And we have something here special. We have a UV transposition of the UV light into visible light to improve not only the performance, but as well the reliability. Now, today, I'm going to focus on 3 of these things. The first one is the isolation of the edge of the module. We have been using here, and we will keep on using, a material that has 10 times the resistance to water vapor transmission compared to POE. POE is widely acknowledged to be the material that protects best against water ingress. And we put all around the module a layer that protects 10 times more compared to this POE. The result is what you see on the right side. This is a lifetime, we call this a lifetime analysis. So we go to do, and I somehow don't see this. Let me see. Yeah. We don't perform DH1000. We perform DH6000. I took from Sinovoltaics, from the company, their description of what is DH1000. This is the test that describes several years of operation in humid countries, and we do as DH6000. If you remember what you have seen today, most of the analysis for the really long term that you have seen on screen were DH3000. I even took the liberty to cut very quickly a print screen of Inco's presentation. I hope it's all right, Inco. I just cut it live. And I wanted to show you the test result that they were doing compared to what we do. So the red light is at -4%. We don't even reach that degradation in our DH6000, as you can see with many of the modules, and they reach a stability. We do DH6000. I'm gonna show it here again. I put the same degradation level of 4% in the graph of Inco, and I put the vertical final 5000 that they perform here. So this is a way to show you how good the result is and how proud we are about doing this advancement in the technology. It's even so that we are releasing a module because of this very good resistance to water ingress that is for floating systems on salty water. The reality, because of waves, is that this will be mostly applied for brackish water nearby the sea, but this is something that we are looking forward to customers coming to us to expand the application field of photovoltaic to environments that as of today are maybe so harsh that developers don't trust to put the modules in there. Now, the second point is what personally I think is very, very exciting, because I remember talking about this 18 years ago with our people in research of heterojunction. And at the time, they told me that it was not something they could do, and now we can do it. We put in our encapsulant a characteristic that translates or converts some of the spectrum that is in the UV light into visible light. This has two results. The first one is that the efficiency is better because the conversion efficiency in the visible light is better than in the UV. And the second is that we protect the module against UV. When I say protect the module, it's mostly to protect the PN junction from having the passivation damaged by UV irradiance. This is something that today we didn't touch a lot, and we don't have time to talk about too much. But generally speaking, UV light has so much energy that it can damage the passivation layers that are put into the module to protect or to improve the efficiency of the cell. So over time, you can have a degradation. Here again, what we perform is a lifetime test. So we go way beyond the duration of the test of the typical long-term degradation test. And still we have degradation values that are really, really low, as you can see on screen. Finally, UV 180. Finally, I want to talk about this flexibility of the cell, because this sounds very generic. But if you have seen us in any exhibition, we typically have cells in our hands that you can touch. We were last week in England, and basically when a cell is very, very thin, and when a cell is done in a symmetrical way without laser damaging, you can flex it without any microcracks. The final result of this for us is that when you have a heterojunction cell already today with 120 micrometers, and even more when we go to 100 or to 90 micrometers next year, you will have a cell that basically bends without microcracks. The result for you or for the user is that it's gonna bend better than the glass. So when you look at your PV system, if the glass is not broken, your cells are fine. So this is to reduce one of the worries and one of the problems that you see on the field, and to pass the problem to the mechanical design of the module. And now I want to not steal, but quote our colleagues, maybe from Trina. There has been done a lot of work on the mechanical design of large modules with different aluminum alloys and different frame designs. And now we can reach extremely high mechanical loads without any problem on glass modules. With that, I finished the introduction about the reliability and generally about heterojunction. I want to tell you what's coming next. We are right now, I'm sorry, the slide, maybe the letters are very small. I hope your screens are big enough. We find ourselves in heterojunction. Yes,
Christian, you have to really wrap up.
this is the last one, so I'm happy about that. The only point I want to make here is that we will apply next year some increases in efficiency mostly. And for the horizon of 2 years from now, we are going to be showing to you tandem modules with heterojunction and perovskite. So, thank you very much. The slide before, in case you were curious, is just our 350 megawatt project in Bulgaria, one of the many utility scale projects that are have been delivered already and are being delivered. And for any question, we will be in the chat and we'll give you some answers. Thank you very much.
Yeah, absolutely. I was also going to say the same because there are some questions and I think someone is already answering on your behalf in the chat window. That's a great arrangement. So thanks a lot, Christian. I think since you overboarded a little bit in terms of time, so I will just move to the next presentation.